Hi everyone, I am Yefei Wang, a computer engineering major at the University of Michigan. Today, I'm going to present you the embedded implementation of the Van der Pol oscillator. In reality, several factors prevent simple harmonic oscillators from stably running, as we can see from this graph. The problems are many. On the software side, there are computational delays and quantization errors that makes the calculation of the oscillation not as accurate as is expected. And on the hardware side, we have nonlinear dynamics and encoder resolution that either contributes to the quantization error or it makes the movement of the oscillator itself not so predictable. Therefore, it calls for nonlinear damping. One perfect example of nonlinear damping is the Van der Pol oscillator, given by the formula below. It is self-stabilizing because, as we can see from the damping term, at a very small amplitude, it tend to go unstable, and at a large amplitude, it tend to go back. So theoretically, wherever we start, we can eventually reach this circle as is shown on the presentation, which is called the limit cycle. And we have two controllable parameters, the epsilon that controls the damping term and the omega square that controls both the amplitude and the period. To implement this oscillator, we are given the following hardware. First, we have a Freescale MPC 5553 microprocessor, and we have a haptic box connected to the microprocessor, which contains an encoder for position measurement and a motor and a hand wheel. To command the motor, we have a motor controller and power unit. And for the software side, we have MATLAB with Simulink. Because of its amazing analytical capabilities, we have data acquisition program, data analysis program, and theoretical simulation scripts, both right in MATLAB with Simulink. And for the main program, to control the motor and to transmit the data, we're using embedded C. We have done tons of experiments with different epsilon and different omega. Here are one set of contrast data. The left is experimental and the right is predicted data. We can see that from these graphs, the oscillator is running pretty much predictable. However, there are a few issues in this oscillator. First, in order to implement it, we need a system identification to find the dynamics of the system from a control perspective in order to compensate the nonlinearities. And second, we need a parameter choosing. If it's too small, it tends to be trapped in a dead zone. If it's too large, it will go beyond the limit so that the motor can afford. And we need to adjust the hardware so as to eliminate the nonlinearities as much as possible. These will be done in future work. That concludes my presentation. Thank you for your attention.